Hello everyone, I am Shyam and this is my project for PHC 351 Fundamentals of AI. And my project is reinforcement learning for adaptive trajectory optimization and orbital control in spaceflight dynamics. So, when we talk about spaceflight dynamics, in this domain, the scope of error is so much and there could be endless possibilities, and often whatever we predict through theory doesn't happen because it's not ideal. We could face so many unexpected situations and everything. So while modeling a spacecraft's trajectory or path planning, the classical methods are actually out of the equation because it fails to capture the entire complexity. For example, we could see the two body and three body problems for physics and all the space related problems, where the classical techniques become like exponentially more tedious to perform. So we could go for ML techniques. In ML techniques, all the linear models or all the classical ML models, those can't capture the entire complexity of this spaceflight dynamics problems. So we could either go for a neural net, but that is difficult to train with the type of data we get in spaceflight dynamics. So I have opted to take reinforcement learning for this topic. Reinforcement learning is like a child, which yeah, it could be like symbolized as a child, which we reward for good actions and punish for bad actions that we define. So basically, we will okay. Let's go about it and see. Yeah, why reinforcement learning for orbit transfers? Traditional orbital maneuver planning include like Hohmann and bielliptic transfers. That is, from circular orbits we go to higher circular orbits. Relies on analytical numerical optimizations under idealistic assumptions. So, impulsive thrust delivery, two body dynamics, and deterministic environments. However, yeah, real spacecrafts operate in non-linear fashion, and we have perturbed conditions, and not everything that happens in a spacecraft is ideal. So we need some sort of a corrective measure for this. So which doesn't like we don't get those from classical techniques. So reinforcement learning provides a model-free control paradigm that learns optimal policies directly from interaction with the environment. So we create a realistic physics engine, or we adopt a realistic physics engine, and through which we run simulations, and through simulations we train the reinforcement learning model. So at start it doesn't know anything. So we create a state. I mean, we define states for the policy. Like policy is the model. So we define states for it, and we define what actions it should take, and we define the reward it will get if we if that performs those actions. So by framing the orbital transfer as a sequential decision making process, which is a sequential decision making process, RL agents can discover adaptive, fuel efficient trajectories that generalize across varying orbital conditions and system parameters. Well, the advantages range from direct learning of continuous thrust profiles from experience, and then to like non-ideal cases and multi-objective optimization. That is, the constraint equations become way more difficult when when we are optimizing multiple things. So that is getting solved here. And then no explicit optimal control equations required. Yeah, we don't deal with the equations. The parameter itself learns it through the approximation theorem. Yeah, let's see about the orbital mechanics and transfer types first. In orbital motion in two-body gravitational field follows Newton's laws. So we are taking Newton's laws over here, as you could see. R dot is V and V dot is mu by R cube into R plus T by M. And we have these orbital mechanics equations over here. Well, let's go about Hohmann transfer. So here we have two burn maneuver. First we have a circular orbit, and from the circular orbit we thrust our spacecraft to go into an elliptical orbit, and it goes on an elliptical orbit, and when it is at the apogee, that is the farthest point in the elliptical orbit, we again give a thrust to make that as the circular orbit. So in that way it goes from a lower orbit to higher orbit. And by elliptic transfer is a three burn sequence through an intermediate apogee. It's like more efficient than Hohmann when the radius ratio exceeds minus 11.94. But Hohmann transfer is very good for low thrust cases, which is for the ratio which is less than 11.94. So yeah, we usually go for Hohmann transfer, and in this particular project I have implemented Hohmann transfer. And then there is also plane change transfer, which is like which changes the plane at which the orbit occurs. So we we go out of plane and change the direction of the plane. Let's go into reinforcement learning fundamentals first. Okay, we are going to do orbital mechanics through reinforcement learning. So let's see what it is. So reinforcement learning formulates sequential decision making process as Markov decision process. So Markov decision process is uh, so it has a state. So we have a model which is at a state. There could be multiple states, and then we have actions which the model takes at that state to go to a next state. So we have a state, we take action, we go to another state. So this is like a sequential process that happens, and what decides what action we take is actually the rewards. So based on the rewards and punishment it gets, it changes that. And in Markov decision process, it is a rule that it only depends on the previous state and action, not anything before that. So it only directly depends on the just previous state and action. So we have this A is the action space, S is the state space, and the transition dynamics, which is actually a policy. Policy is our model actually. That policy decides how we should move. And then RC is the scale reward function, and then gamma. This discount factor is a concept such that, okay, when we get rewards, the rewards is defined such as we get the reward for the next time step t and the next one and the next one till the end of the simulation. So we account for rewards that we get all along the way in the future. And discount factor is such that it is every term is multiplied by gamma, gamma square, gamma cube, and so on, like the geometry progression. So by adjusting gamma, we could decide between having long-term gains and short-term gains. So that's what gamma is used for, and gamma is hyperparameter. And MDP properties we could see here. Markov property, future states only depend on current state, action, not history, is the immediate state and action. And then episode. One episode could be said as one particular simulation. Let's assume a mob trying to clean the floor, and it's using RL. So one session of cleaning could be said as episode. And each episode will have multiple steps. That is, it's basically the steps the model takes. And learning paradigm is trial and error, the most simplest form of learning. And optimization is via the reward feedback. So when we do trial and error, so based on the attempt, we get a reward or punishment, and based on that, we update the parameters of the model. So generalization. Since we are doing trial and error, it learns patterns that are unseen to all other types of model, that in which we give a specific data, which could be biased. And let's see RL components in orbital transfer context. Mapping the abstract RL framework is careful definition of each MDP component. So let's see, that's what I already explained. It's we have a component of state, which okay, in our case, in our orbital transfer context, state is the orbital position r, the velocity v, and the remaining propellant mass m, which captures the complete state, like the complete instantaneous orbital configuration, which is encoded in a 7-dimensional vector. That is, we have position in x, y, and z plane, and velocity in x, y, and z plane, and we have mass. And let's see the action. That is the continuous thrust we are going to give, and the magnitude and direction that it is being given. So our output will be in a 3-dimensional vector, that is acceleration in x, y, and z, from which we can also take the magnitude whenever we want. And then reward. This is the most important part of the model. This literally defines how the model will work. So this reward, I have set a definite reward for our model in this project, which we will come to it later. And then policy. Policy is the model, like that is the, we could consider the brain of a project. So it's just basically a neural network mapping states to thrust action distributions. So all the parameters in those neural networks are modified and changed by this reward. So we define the state, action, and reward, and policy, everything. So let's go to categories of reinforcement learning algorithms. So RL algorithms are majorly classified into model-based and model-free. So in model-based, even the environment itself is modeled into the network. So in model-free, such as PPO, proximal policy optimization, which is the model we use right now, and DD3 and all that, we only model the state to action. But in the model based, we also model the environment into the network itself. And then we have value based and policy based. Let's go first by policy based. Policies, as we said, is the actual model and actual brain of our project. So this model, policy based, so apparently what we do is we perform actions and we see the rewards, and based on it we update the policy itself. And then in value based models we do this. What happens is value is basically the expected return for a particular action. So what we do is for each action we try to estimate the value, what value will we get for that action. That is value based. And actor critic model, that is actually a PPO also comes under that, in which we have policy and value. So the policy acts as an actor and the value acts as a critic. So that is like a game of cat and mouse. So let's come to it later. So Q is the actual return that we get. That is y to the power t into rt, which is which is like a conditional probability which depends on state and action, and we take the expectation of it. So yeah, let's see about policy gradient function foundations now. Okay, so our model PPO is based on policy gradient only. So what we do is we take the gradient of the loss. No, we take the gradient of the policy. That is, action T given we are in a state AT, a state ST. What happens is we take actions AT given that we are in a particular state, so which is dependent on the state. So we have conditional probability, and that is multiplied by a log, that is for computational easiness. So what happens is we compute the loss after the log, and we multiply by a factor called advantage AT. So this advantage, this for proximal policy optimization, this advantage AT could be described in this way. For example, our policy gives us a output distribution of probabilities. That let's assume we have 3 actions. It gives probability for all those 3 actions, which have certain probabilities. But we just know that one of the action is right. So this advantage AT scales that one probability to maximum and decreases the other 2. And how it does is, advantage could be described as advantage is a measure of saying how much our action that we currently took is better than the average action. So yeah, here it is given. Measures how much better action AT performs relative to the policy's average behavior in a state ST. So yeah, this is what it is. Q is the actual return and V is the expected. Value is literally the expected returns. So positive advantage indicates the action outperforms baseline expectations, and negative suggests inferior performance. So based on this, we scale the policy's outputs. So yeah, for estimating this particular output, what are the particular return and reward what we get. So we could do it using Monte Carlo simulation. Just going out to the simulation and see what we are getting, and we have this expected value already using this computational methods. Or we could go with a temporal difference method. That is, we will be bootstrapping the value to estimate Q. So we'll be doing that using value of S of t plus 1 from and so on. So we take the temporal difference. That is a way to make it easier. And the generalized advantage estimation is, it interpolates between Monte Carlo and TD methods using hyperparameter lambda between 0 and 1. Yeah, so this is what the actual advantage that we get. So proximal policy optimization. This is a clipping mechanism. Okay, what happens is we optimize the policy in this. Okay, usually in case of neural networks we do back propagation and do gradient descent. So for policy optimization we could use this method so that the parameters of the policy doesn't change very drastically and go off too far. So we maintain a stable differences. So for that we have this clipping function. L clip of theta will be given as minimum of RT's returns. So RT of theta 80, comma clip of, this is the equation, and where the probability ratio is defined as RT theta of policy theta of, this is policy theta and policy theta old. What happens is, actually when practically running these simulations, we run a set of trajectories and we try to calculate the losses and we try to optimize it. But what we do is, instead of computing these trajectories each and every time, we take the concept of reuse. Like we reuse data in supervised learning and for multiple epochs. So like that we reuse. But these trajectories are decided by old parameters, and after updating the new parameters, we can't use it statistically. So for that, For that, there's a mechanism in the laws. So yeah, we this is like a general overview of it. Now we come to the PPO, actually training cycle. So what happens is a rollout collection. Generate trajectories using current policy p theta, old. So loss function of the value. The value loss function is given by the expected value minus the returns. So we take the expected value of that, and then entropy regularization also we do, because it maximizes exploration. It encourages the exploration, and then we do the combined objective. LPPO is equal to LClip, and we also add the additional entropy regularization and also the value function loss. So yeah, multi-epoch optimization is also happening here. Meta reinforcement learning for rapid adaptation. Yeah. So we use PPO model, but we also use Meta RL. Meta RL could be described in this way. So standard RL learns to do a specific job. Meta RL learns how to learn. So it basically is used for generalization and adaptation. So using this, the model adapts really quickly to changes, and then it's really helpful for generalization, which is very important in case of orbital mechanics. So here in the inner loop, task specific adaptations happen. We could have multiple tasks in a orbital mechanics situation. So all those tasks happen and RL mechanics happen inside those. So here I have used PPO for that. I have defined two tasks, and for two tasks we have PPO models running, two PPO models, and in the outer loop the meta optimization runs. Optimize the initialization theta to maximum post adaptation loss across all tasks. So we have this parameter updation for inner loops, and here we optimize the parameters to minimize the post adaptation loss. So model agnostic meta learning, MAML. So MAML instantiates the framework for neural network policies. The meta learned initialization serves as a strong prior, requiring only 5 to 10 gradient steps to adapt. In case of like non-MAML cases, we'll be like using so many gradient steps. So this decreases it by a lot, and it's used for generalization, and it's also helpful in adaptation. So let's see how it helps us. So meta RL paradigms for spacecraft autonomy could be gradient based, recurrent based, and latent contextual. But we are using gradient based because we use PPO, that is a policy gradient method. So learn optimal initialization parameters that enable rapid adaptation through few gradient steps. So that's what we are doing. Here in recurrent based, we use memory augmented networks that encode task context over episodes. So it does a context based approach. And here in contextual, learn compressed task embeddings in latent space for efficient context representation. So these both are not really applicable for our tasks. So we are using gradient based. An application to orbital transfer problems. In our orbital transfer environment, meta learning addresses the challenge of mission variability. The task distribution comprises transfers from low Earth orbit to geo Earth orbit to different inclinations also it can be there, and heterogeneous thrust capabilities. So, and there could be multiple tasks. In my particular case, I have defined one for general thrust and another for drag and perturbation. So we have these two models which come under the meta RL learning. And next I have also implemented safe reinforcement learning. That is, we have this general reward and punishment mechanism inside our RL already. But in case of safe RL, I add extra constraints that ensure the absolute safety. The thing is, we maximize the returns here. Subject to I also add extra constraints such that CT represents the constraint cost at time step t. So that's what we do. So for example, the safety constraints in orbital environment that I have implemented is altitude below low Earth orbit, because we have to shift higher. We shouldn't go down like in any case. So I have kept the threshold to be this. So if the penalty action is episode termination and minus 1000 reward, and fuel depletion should absolutely not happen. Well, I have defined fuel in terms of kg. My spacecraft will be like 500 kgs, and when fuel runs out, the mass of the spacecraft decreases. So through which I have defined this. If that drops below 100 kgs, then 500 negative 500 reward, and I'd be like ending the episode. And then for time limit exciting also. The thing is, it can't take forever to go switch orbits. So we have also episode truncation and but no penalty, like in such way. So let's see about the reward structure that we have made over here. So we have differential rewards over here, delta D by ST. And then WD is the parameter, like a hyperparameter that we could tune. I mean, the entire reward function itself is chosen by us, but WD is a parameter that is tunable. WE is also tunable. Delta E gives the energy difference between the orbits. Delta T is distance progress. It measures the R previous minus R target minus R minus R target. And here is the energy optimization, delta E, that is given by this particular equation that we have chosen. And then we have WFFT, that is fuel conservation. Like as we said, like the less fuel conserved is the better. And then we have thrust alignment. Yeah, the thrust should be aligned with the velocity vector, because if it's not aligned, we have fuel wastage and we need to correct the track again. Yeah, let's see the terminal rewards and penalties apart from this. Because after the orbit has been reached, it shouldn't fall down randomly. So it should maintain that orbit. So success bonus, once we have successfully shifted the orbits, 150 plus 150 is awarded when circulation is achieved within a tolerance of 1000 meters. And yeah, altitude violation, yeah, unsafe. We have seen about this fuel depletion and control cost, all the safety parameters. Yeah, so that's all about the reward structure. And then implementation. Let's come out about the implementation what we have done. The custom gymnasium interface with Polyastro. Polyastro is the module we have used for as the physics engine, but it has a limitation that it can't run on a GPU. So I had to train it with the CPU, but I used parallelization in running scenarios, in running this trajectory, such that I could run around 6 to 8 trajectories at a time parallelly in my CPU. So for propagator, Covell numerical integrator with adaptive step size. I have also used RK4, Range-Kutta 4 method as a fallback for high fidelity force modeling. And then algorithm. We have used proximal policy optimization as the heart of our model. We have defined 2 tasks with it, and we have used the meta RL on top of that. So yeah, the architecture is actor critic model, such that the actor here is the policy which acts, and critic is the value function, which estimates the value for that particular action. So it acts like a critic, and the policy acts like an actor. Yeah, so with safety constraints and so on. Right, and this. So let's come to the conclusions and future research directions. We have done effective policy learning through PPO. PPO is actually founded by um, the ChatGPT's founders team, but it actually was a replacement for TRPO, which is given by DeepSeek. So TRPO segregates into trusted regions, segregates the policy gradient map into trusted regions so that the gradients aren't too unstable. But this PPO does it with the simpler mathematics, the same tasks. And yeah, we have safety, critical operations, rapid adaptation, and then the future research directions can go by multi-agent coordination. Now we are dealing with one particular spacecraft. Later we could go on and do the same for multiple, and complex maneuvers, by elliptic transfers and plane change maneuvers and so on, and adaptive replanning. For example, if the spacecraft goes off course and we need to correct it, we could go about that. So fine, yeah, let's go about the code right now, the code we have written. So first, let's start with the environment. I have initialized the environment from Covell Orbit ENV, that is from Polyastro. So we have we have imported gymnasium, NumPy, and all the modules that are required, and we start the environment. And here we define the environment properly. This Earth gravitational constant, and then TT is the time step for our simulation, which is if I'm right, yeah, 1 second over here. and we give max steps 4000 steps over here for the episodes. And then an action space, this is our this is action space is the acceleration outputs, ax, ay, and az. And observation space is the inputs rx, ry, rz, and mass. And so it's like a seven-dimensional vector, like I mentioned before. So initialization, we initialize the state, and then we create a function for resetting the environment after episodes. And then we have a RK4 fallback. This was primarily created because when I was using Cobol, I faced 2 to 3 times my program crashed while training. So my CPU wasn't good enough to handle this. So I also had a RK4 fallback, which is computationally friendly. Just in case the Cobol doesn't work as expected, this switches back to RK4. And then we have this Cobol step, which is the primary integrator we are using and propagator for our all physics-based problems over here. And then we have the thrust perturbation within the Cobol module. So yeah, this gives us the measure of like propagation, like how the new state should be. All the new states are like calculated over here from the previous states. Acceleration in kilometer square, kilometer per meter per second square is given over here. And then here we come to the step plus reward, get observation. This is to get the current numpy array of the state vectors, that is used for reinforcement learning training. And here is a step vector, that defines the steps. So we here take the previous state and previous everything, all the RVM, and then the targets, the previous distances, previous energies, and everything. And we define the next states and for the particular steps. And here we come to the reward functions, differential progress terms, as we have seen in the PPT. For the distance reduction and energy reduction, we have taken the differential terms. The reason why I took differential terms was, if it was linear, it doesn't have a measure of if it's going okay. Assume I have to go on the right side for my distance to be reduced, but if I go right side, I will get a reward, but I don't know in which direction and right. So if I have this differential error, as I get close to the goal, my rewards keep getting bigger linearly. So this way it helps the model. And this sort of reward is way more proper for this application. And we have all these parameters that is tunable, and we have fuel used and reward. So here I have in comments I have mentioned the entire process. Distance based reward is over here, energy progress reward, and then alignment reward for the theta, and then terminal success, we get a huge bonus if we do that. And then we have fuel usage penalty, direct action penalty, crash penalty, fuel depletion penalty, time limit penalty. And after it goes into a stable orbit, it needs to maintain it, so even we have a reward for that. So our environment is over. We could just go about the agents right now. So we could go about the meta RL, the overall meta RL that we are using. So we have this int of 2 lakh steps over here, and meta epochs is 5. For each multiple inner loops, one outer loop is trained. After many inner loops of tasks have been performed, the adaptation takes place in meta RL. So we have this learning rate. Okay, the thing is, the meta RL requires many hyperparameters which are taken from here config.yml. Here I have given all the hyperparameters that are needed, and all the number of epochs and every sort of parameter that is needed, and that I have called in here, and I have ensured it's a float and not a string. So then we initialize the model over here, and I get a vectorized environment so that I could run in multiple trajectories in parallel in my CPU. Then inside that we create a PPO model. The meta model itself is a PPO model, and the meta model training loop happens over here, and in which the meta update policy is also given over here. Well, okay, this is done. Let's go to the PPO agent. That is the heart of the project. This is like a relatively short code because we have done a standard code right here. So we have imported all the required things over here, and then we have made a vectorized environment, and then I'm building the PPO agent safely inside the main. And here I'm using MLP policy, and then we have set a gamma value of 0.99. The reason we set gamma as 0.99 is higher the gamma, we focus more on long-term goals than short-term goals. If it is around zero point 0.5 or something lesser, so that means we are focusing more on short term goals. This works well on financial forecasts and using RL for those sort of tasks. But in case of space tasks, we would be focusing more on long term goals. So then we define the batch size over here and the number of epochs and everything. And then I have created a safety layer functions for that. This is basically the code of whatever I have mentioned in the PPT. For R, and okay, for R I have created three-dimensional array, and sorry, one D array, but with three parameters and all that. And this is what it describes. And we have model checkpoints and everything that is needed. And let's go to the main part of the codes. Like, okay, let's go to the training code right now. This makes an environment, um, like trains the meta agent, and inside which, sorry, yeah, inside which it has, the meta model is described over here. And then inside it has two tasks, as I said. One is orbit transfer and another is drag and perturbation. So we have created model checkpoints during training. And also, yeah, for each meta epoch, the both of these agents are trained, like iteratively. So here also, even those two agents are made up of, adapted models for task in tasks. Each task is also a PPO model, which is actually MLP. And then we have this meta update room over here. How the meta update is happening over here, that is described in here. And then, yeah, once my training is done, we'll be evaluating the model. Here is my evaluation code. This evaluate model takes the trajectory, it sees the, it initiates the total reward to be 0 0, and it parses through multiple steps. This number of steps is defined by me. And then, in the each trajectory, it is appending all these, and it is processing all these steps. And after processing all these steps, it gives the evaluation results, such as my let's just see here now. Let's just run it and see here. Yeah, for your information, yeah, the safe meta RL final zip. What happens is, for each epoch I train this model, it is stored as a zip for each epoch. So we are getting a progressively better models over there. So the final safe meta is the best one which I have chosen. And as you can see, the steps are progressed and the distance is shown over here. And then the reward function is also shown over here, which finally sort of fluctuates a little bit and decreases. Okay, what actually happened was, what I discovered is that the number of epochs trained with my laptop has a limitation. I trained it for 8 epochs. That's what I could do with the limitations of my laptop. But if I had trained for like 4 epochs, which I had already tried, the reward is actually it was decreasing. Okay, this is a negative. So which means that our model is progressing towards a better side. In the 4 epochs case, it was not so good. It was decreasing. And then when I trained for 8 epochs, it's fairly well, but it's not good enough. And as we could train higher and higher, it gets better. The reward function is really good, what we have defined over here. It's just a matter of number of epochs that we could run. So in my laptop, this is the limitation. I could run it for 8 epochs. And this is the reward we get, the total cumulative reward. And cumulative reward, we could actually take the mean of it and make sense of it. And yeah, we have the velocity different and for each time step. So we could define the number of time steps that we need. And I have also written a visualization code over here, which visualizes the model. Let me just show you real quick. Yeah, Earth plus orbit rings. We create a Earth sort of figure, and we have orbit rings, the low Earth orbit and geo-Earth orbit. And we give it a blue color, and we initiate the target radius. The initial radius is this much and target is this much. That is multiplied into 10 power 6 meters. And we are getting the plots over here, and actual trajectory is mapped over here. So yeah, and the ideal home and transfer ellipse is also shown over here. We'll be able to see that. Let me run the visualization real quick. Yep, here we can see the visualization. Okay, what actually happened is okay, I'll be not able to zoom in into this one. Well, the green the green one is the home and transfer. It gradually shifts into the red. Red is the target orbit, and green is the initial orbit. And it is supposed to be like jumping real quick from here to here. But since our model is not didn't run for enough number of epochs, the reward is good. It takes really long. It is slightly shifting from the green orbit. It is going towards the red orbit, but it is not. It has not yet arrived over here. And yeah, reward engineering is very important in this. And yeah, with enough number of epochs, it will eventually reach over there. The thing is, we have defined home and transfer over here. And as a future note, we could um, we could go on to elliptical orbits and plane change orbits also. And yeah, once I do this, I have also this eval diagnostics. I also get this diagnostics as a result. And I have this YAML, and I have a properly divided all these into this videos. Sorry, not videos. Divided into these proper folders, like visualization results. Everything is getting saved, and apart from all that, we have put folders and everything in a proper place. So yeah, that's my project for here. So hope you liked it. Bye guys.